he is going to talk about magic squares today. Ryan?
Thank you, Mr. Lee. I appreciate this opportunity to share my excitement about mathematics with all of you. I ran across magic squares for the first time this summer in a class entitled Math and the Arts. So most people think math and art, what in the world do those have to do with each other? So I took a whole class on the fact that they do have an awful lot to do with each other, in fact. And we were presented with this engraving. It's by a man named Durer. I'm probably butchering his name. And it was engraved in 1514. And among many things, there's some political statements going on here. There's some religious statements going on here. But since this is a math talk, we're going to talk about the math going on here. If you notice up in this upper right-hand corner, you can kind of make out an outline of something. So I zoomed in on that. And you can see, of course, the top of the angel's wings, and there's a bell, an hourglass, and a scale, which these things have quite a bit to do with mathematics. What I'm most interested in on this engraving that's in the side of the wall here. So I'm going to zoom in on that, and we can see this array of numbers. And the first thing that I notice is that each whole number from 1 to 16 is used. And the second thing I notice is that he created this in 1514 and he incorporated that into his engraving. This thing is a little difficult to read, so what I did was copied those numbers and put it like this so it's a little easier to see what's going on. And the next thing that's interesting is that each column, in this case row, add up to 34. Each column adds up to 34. And each main diagonal adds up to 34. So this thing is called a magic square. And specifically, it's called a normal magic square. The size of the magic square is the number of rows in the square, and since it's a square, also the number of columns in the square. And we call this an n by n magic square. And in this case, it's a 4 by 4 magic square. It's called normal if it meets two conditions. The first condition is that if you think of number 1 as being the first number, and the 4 by 4, 4 being the n number, then n squared is 16. And 1 to n squared is 1 to 4 squared, which is 1 to 16, and each of the numbers is being used, whole numbers, from 1 to 16. The second condition is that each row, each column, and the main diagonals all add up to what's called the magic constant. Sometimes we call it the magic number, and that's what I will refer to it from now on as the magic number. And in this case, that magic number is 34. Sometimes normal magic squares have additional magic, and in Durer's magic square, each of the corners add up to 34. Each of the corner blocks add up to 34, and the middle block adds up to 34. Durer did this in 1514, and I can guarantee you he did it without the use of a computer. So let's create our own magic square. That'd be fun, right? We're talking about magic squares. Let's make our own. This is a 1 by 1 magic square, and its magic number is 1. Great. Well, that's not very exciting. This is referred to as the trivial magic square, which, as you see, why it's trivial, not very exciting. So moving on to 2 by 2. So I'm going to put all the whole numbers from 1 to 4. And I notice right away I have trouble, because 3 plus 4 makes 7. Very good. And 3 plus 1 makes 4. So I somehow have to get 4 and 7 in some arrangement to equal each other. And no matter how I put this, I'm still going to have 3 plus 4 equals 7. And 3 plus 1 equals, so I'm in trouble, right? So as it turns out, there's no 2 by 2 magic square. Now we're going to move on to 3 by 3. This is the good stuff. Okay, so who can tell me how many whole numbers we need in a 3 by 3? Go ahead.
9.
You need 9, very good. So we're going to use that idea to identify the magic number. That's really important for us. And we're going to borrow somebody's idea. His name was Gauss. Now, Gauss died in 1855, so this was quite a while ago. As the story goes, when Gauss was in grade school, he was asked, along with all his fellow students, to add up all the numbers from 1 to 100, all the whole numbers. And as the story goes, the professor, or the teacher I suppose, sat down at his desk hoping to sort of relax for the next half hour, 45 minutes while all the students added up 1 plus 2 is 3. Okay, so then 3 plus 2 and on and on. Well, the story goes that almost immediately Gauss went up with his tablet, his chalk tablet, and put it on the desk with this number. And as it turns out, that's correct. If I add up all the whole numbers from 1 to 100, it's 50-50. Well, the instructor asked his student, how in the world did you come up with that so fast? And it turns out Gauss had thought about this before. And he said, well, here's the thing. If I list all the numbers out from 1 to 100, 1 plus 2 plus 3 plus 4 plus ... all the way up to 97, 98, 99, 100, and I do the same thing in the other direction. So I go 1 plus 2 plus 3 plus 4 plus ... 98, 99, 100. I notice that all the columns add up to 101. Pretty ingenious for a grade schooler. And of course, I have 100 sets of 100. And if you have 100 sets of 100, you can multiply them together, divide it by 2, and that turns out to be 100 times 100 plus 1 divided by 2. And in general, if you take the first number and the mth number, that's m times n plus 1 divided by 2. And in our case, he was asked from 1 to 100, so he said m times n plus 1, so 100 plus 100 plus 1, which is 101, divided by 2 is 50-50. So in general, we can use this idea that Gauss came up with. From 1 to n squared, in our case 9, is 1 to 3 squared, which is 1 to 9 squared. So that's 9 plus 1 divided by 2, so 9 times 10 divided by 2. But because again, 9, remember, is the same thing as n squared, this is 9 squared plus 1 divided by 2. So that equals 45. So if we add up all these numbers, we have 45. But we want each row and column, and there are 3 of those, so we need to divide that by a third, or multiply it by a third, and that equals 15. So the magic number of this 3 by 3 square is 15. As it turns out, we can generalize this formula. Because again, we're talking about n squared times n squared plus 1 divided by 2 multiplied by 1 over n. This n and one of those n's simplify to become this general formula. So that's n times n squared plus 1 divided by 2. This will tell us the magic number of any magic square. And if we plug these numbers in directly, we get 3 times 10 divided by 2, which is 15. So we know our magic number is 15. Next, we can do a little careful deduction to figure out what this middle number has to be. I'm going to call it C for a minute. And notice that I'm going to use C plus 2 numbers to equal the magic number, that's 15. I use it again here, I use it here, and here. I use it 4 times. So 15 plus 15 plus 15 will equal 60. C makes up 4 of these. So one of the C's is in here, adding up the numbers from 1 to 9, and then I have 3 others. Using Gauss's idea again for 1 to 9, I have 9 times 10 divided by 2. Simplifying this, this is 3C plus 45 is equal to 60. I can solve that. I minus 45 from both sides. I have 3C equals 15. I divide both sides by 3, and C is equal to 15, or 5. So I know the middle number of my 3 by 3 magic square has to be 5. Let's think about one more clue. If I take the number 9, I have to add it to 2 whole numbers and equal 15. So 9 plus 1 plus 5 is 15. 9 plus 2 plus 4 is 15. 9 plus 3 plus 3 is equal to 15. 9 plus 4 plus 2 is 15. 9 plus 5 plus 1 is 15. And 9 plus 6 plus 0 is 15. I don't need to go on because 9 plus 7 is more than 15, so I'd have to go backwards. And as it turns out, I can throw out this one because I would have to use 3 twice, and the rule says I only use it once. And I don't have a 0 anyways, right? So I don't need that one. I can take those 2 out. And who can tell me the property of addition that says this thing is really the same thing as this? Who knows what that is? No one? A room full of math people? What's it called? Go ahead. Commutative property? How does that sound? Commutative? Very good. Good job. So 9 plus 4 plus 2 is really the same thing as 9 plus 2 plus 4. So these 4 really are just those 2, right? So what does that tell me? That 9 only gets used twice. So if I put it in a corner, I'm in trouble, right? Because it would have to get used once, twice, 3 times. That means 9 cannot be in a corner. And if it can't be in a corner, and it can't be in the middle, because 5's already there, it has to be here, or here, or here, or there. So 9 must be in one of the middles. So now we have these ideas. We have a middle, which is 5. The whole thing has to add up to 15. And we know that the corners can't be 9. So let's take a few minutes on your little cheat sheet there. You can put in 5 in the middle and see if we can come up with our magic squares. No cheating, Mr. Dersh. No? Oh, okay. Sometimes trial and error is the best way to do it. It's always fun having to do addition on the spot, right? You have to really think about. How we doing? Do we have one over here? Good. It looks good. So we've got 2 solutions. Oh, you want a new pencil? Oh, I can probably handle that too. Oh, you got it, Mr. Dersh? Thanks. Yep. Looks really good, I think. All right. So you guys, folks can work on this for the rest of the day at home over Christmas break. Wouldn't that be fun to work on magic squares over Christmas break? 10 by 10. 10 by 10, yeah. All right. So as it turns out, we can find 8 possible solutions. All right? And these are the 8. But on closer inspection, are they really 8 different things? So for example, I just happened to choose this one first. 8, 1, 6, 7, 2 always sort of appear in that order on the corner. Everyone see that? So I've got 8, 1, 6, 7, 2. And in every square, I see the same, 8, 1, 6, 7, 2. 8, 1, 6, 7, 2. Or, for example, 4, 5, 6 always appear together. Notice, 4, 5, 6 together. 4, 5, 6 together. 4, 5, 6 together. So as it turns out, if I just chose one of them, this one, our initial starting position, RO for initial, fancy there. If I rotated it by 90 degrees, this square becomes this square. So notice, 8 was in the upper left-hand corner. I flipped it over 1, and now it's there. The same is true. Notice 5 doesn't change. It's always in the middle, like a wheel spinning. If I did it twice, well, then 8 moved from there down to here, for example. If I did it 3 times, that'd be 270 degrees. It's just rotated 3 times. And if I did it 4 times, I'd be back to my initial square. This one is reflected around the middle row. So notice, 3, 5, 7 is in the middle, but the 8 and the 4 flip places. Same thing with the 1 and the 9, flip places. If we think about reflecting around the middle column, notice 159 is in the middle, 159 is still in the middle, but the 7 and the 3, for example, just flip places. The same is true for diagonal 1. I called this one diagonal 1. 4, 5, 6 in the middle, and notice 8, 3, and 1 just flip places over on the other side. Same is true for this one, going this way. Well, the 3 by 3 then really only has one solution, right? All the others are just rotations and reflections of the same thing. And if we think of these other rotations or reflections as a group of things, then mathematicians like to give fancy names to things. This group of things has a special name, and it's called a dihedral group of degree 4. That's really fancy stuff. But all that really means is that we call this group of things D4, and there's this list of 8 things in this group. Exciting, right? All right. This is the oldest known example of a magic square. The Chinese legend says the emperor saw this magic square on the back of a turtle in 2200 BC. Now, he didn't see it with the numbers because the Chinese didn't have these numbers, 2200. But what he did see was a rope with a series of knots. So this is 1 knot. This is 5 knots. This is 2 knots. Those of you who are graph theorists, that might ring a bell. A lot of graph theory going on there. It's kind of interesting. This is probably the most famous magic square. It's been around the longest. Okay, so now, I'll let you in on a little secret. There is an algorithm or a trick to constructing any odd numbered magic square. And that's what we're going to do now. This is a 3 by 3, which is odd. If I start in the middle position with a 1, and I do what's called the up and over method, or the over and up method, and I go over 1 and up 1, there's nothing there, right? But if I think of the top and the bottom of the magic square wrapped around and touching each other, like a donut, like you'd wrap it around a donut, then this 2, really, I can put down here. The same idea. If I go over and up, this 3, there's no square there, but if I think of the sides of the magic square being wrapped around and touching each other, then this is really this square. So I can put that there. And then finally, if I go over and up, and the square is already occupied, then I drop it down to here. So the next goes over and up to 5. The next goes over and up to 6. The next goes over and up. But again, if I think of the sides as being rotated around and touching each other, and stretched around the top to being touching each other, this will become this square, which is occupied, so we drop it down 1. The same idea, over and up is this one, and over and up is really that one.
Could you explain again, please, how you get from 3 to 4?
Oh, the drop, okay. So let me back up here a second. This is the hardest part, right? If I go over and up and it's already occupied, then drop it down 1 below. Yep. So that goes there. So over and up is 5, it's not occupied. Over and up is not occupied. But now when I go over and up, it's occupied, so I drop it down 1. Yes, sir?
How did you know to start with 1 in the middle in the center?
Ah, that's the secret. yeah, you have to start with the 1 in the middle on the center.
Okay.
That's the secret.
It could be on any of the edges in the center.
Yes, as long as you think of it, if you start here and
Start there and go.
yeah. But you have to be careful because then you have to think of it as like a reflection, so you have to be a little careful. I always start with it on the top because it's easiest to sort of keep track of what's going on. Yeah. So this makes, in this case, a 3 by 3 magic square. So let's do it for the 5 by 5, right? So we're going to start with the 1 in the middle, and we go over 1 and up 1, and again, the top is wrapped around, so that's really this one down here. I go over and up 1 for 3, over and up 1, the sides are wrapped around, so this becomes this square. Over and up 1 is 5. I go over and up 1 that's occupied already, so I drop down to below. Over and up is 7. Over and up is 8. Over and up is now down here. So far, so good. Over and up is really over here. Over and up is occupied, so that's 11. Over and up is 12, 13, over and up 14, and over and up is 15. Now we have a column, so let's check to see how we're doing. So remember the general formula for a magic square is, for the magic number, is n times n squared plus 1 divided by 2. This is a 5 by 5. So that's 5 times 5 squared plus 1 divided by 2. So this is 5 times 26 divided by 2. I'm going to cancel out the 26 and the 2 to make 13. So I have 5 times 13. 5 times 10 is 50. And 5 times 3 is 15. So that equals 65. How does that look, Mr. Lee? Okay. So my magic number is 65. So now I'm going to do a little Chicago math here. 10, 20, 30, 40, 50. And 5 and 4 makes 9. That's 59. And 2 and 1 makes, I don't know. But then I add 3 and I add 65, right? That's my joke about Chicago math, by the way. So this diagonal adds up to 65. So we ended off here. So we're going to go over 1 and up 1. And that's occupied. So we drop down to 16. We go over 1 and up 1. And then again, it wraps around. And it goes to 17. Over 1 and up 1 is now 18. Same thing, over 1 and up 1 for 19. Over 1 and up 1, 20. Over 1 and up 1 is occupied, so we drop down. We have a row, let's check to make sure it's 65. 10, 20, 30, 40, 50. 1 and makes 60, 3 and 2 makes 65. So we're in good shape. Over and 1 is 22. Over and 1 is this one over here, is 23. 24. And finally 25. So that takes a little practice, right? But it works for any odd number magic square. By the way, you can impress your friends. If you do this with a 3 by 3, you can start with any number. So you say to your friends, give me a number 1 through 100. They say 26. Start with 26 in the middle and use the same for 27, 28, 29 until the magic square is filled, and you'll have a magic square. It's not really a normal magic square, right? Because you're not going 1 through 9, but it's still kind of fun to impress your friends. And if you really do a lot of mental arithmetic, ask them to give you a number from 1 to 100, they'll give you a number, and then you can work backwards, right? So that your magic square equals the number they gave you. All right, is everybody following what I'm saying? But that takes a little practice. And you can look it up online for some practice. Okay, so the question now is, we saw in the 3 by 3 that the magic square was unique for a 3 by 3. So is this 5 by 5 magic square unique? And the answer is, well, no. Here's a counterexample. It's not unique. For example, ours had 11, 12, 13, 14, 15. And notice 11 doesn't have 12 around it anywhere. 12 doesn't have 13 around it anywhere. 14 doesn't have 15 around it anywhere. So these two are unique. So if it's not unique, oh, I'm sorry, I forgot part. There are some similarities though. Each corner with the middle adds up to the magic number. This pattern on both adds up to the magic number. But how many unique 5 by 5 magic squares are there? Would anyone like to guess? Is it more than 7? What do you think? Do you think it's more than 7? More than 10? Well, as it turns out, it's that many. All right, so let me think here. This is 275,305,224. This was discovered by Richard Schroeppel at MIT in 1973. This was when computers were, what can computers do for us? And as it turns out, Mr. Schroeppel and his friends worked in a laboratory that was sponsored by the U.S. Department of Defense, it still is, studying artificial intelligence. Okay? Because if I write a program and I claim it's artificially intelligent, how do you test? Is it really intelligent? All right, well, one way we can do that is say, the computer certainly knows how to add. I've told it how to do that. It certainly knows what equal means, and it certainly knows what whole numbers are. And I say, computer, make me a 3 by 3 array so that you use all the whole numbers from 1 to 9, and they all add up to this columns and rows and diagonals all add up to the same number, without telling the computer an algorithm, and see if the computer can solve that. If it can, that's artificial intelligence. If it can't, Well, how much does the computer really know? Okay? Then if it does it, ask it to do it again and see if it does it faster. That's what we do, right? The second time you're asked to do something, you should probably be able to do it faster than the first. The 20th time you're asked to do something, can you do it faster than the first? So these folks were really thinking about and using magic squares to test artificial intelligence in computers for the U.S. Department of Defense. But this raises a question. If the computer says there's this many, are there really this many? You know, what is proof? Well, I figured it out, and it would take 2 semi-loads full of paper to get, if we printed 20 on front and back 5x5 magic squares, 2 semi-loads to get it from Massachusetts here to Grand Rapids for us to inspect these 200 and some million. It would take us a long time to do that, right? So are there really that many? Well, this is a mathematical question. What really is proof? Can a computer prove things? Maybe it made a mistake. So that's a question to ponder. Here's some other ones. We proved that there was a 1 by 1. There's only one. There's only one 3 by 3. Bessie did it in 1693. On the other side of your handout, when Ben Franklin is communicating with one of his friends about magic squares, he mentions Bessie. There are 880 4x4s. You can read all of those. You can inspect them for yourselves. They're published online. And for 5x5s, there's this enormous number, maybe. Maybe there's more. Maybe the computer made a mistake. For a 6x6, no one knows. No one has any idea. And in fact, if you can solve that question, you'll win a prize. This is an open math question. And any number greater than that, n by n, no one really has any idea. People have used statistics to sort of guess, but no one really knows for sure. Okay, so now let's talk about exotic magic squares. These are the fun ones. I really like these. If we relax the rules a little bit, which means instead of using all the whole numbers from 1 to n squared, maybe we repeat 1 and leave something out. Maybe we use numbers larger than n squared. Or maybe we say the diagonals don't have to add up. So they're still magical, but they're not normal. They're exotic. Okay, so this is Ben Franklin. He is on what bill is Ben Franklin on? Do you know? The $100 bill, that's right, very good. And he, I think, had something to do with writing the Constitution, so he's a pretty important person. Well, as it turns out, his hobby was magic squares. This is not a normal magic square. Its columns and rows all add up to the magic number, but the main diagonals do not. So, it's interesting. This has the corners in the middle add up to the magic number of 260. This sort of half diagonal does. But this is the most fascinating to me, is these bent rows, as he called them. Ben Franklin was certainly able to create a normal magic square, but he found that boring. So he went on to find these other things. So this bent row adds up to the magic number in both directions, in up and down. So if you put it together, it sort of looks like a diagonal. But as it turns out, all of the bent rows add up to the magic number. In the reflection or the wraparound, all add up to the magic number. So the purple adds up to the magic number of all the squares in both directions. So this is, I sort of coded all of them. And this is true up and down as well. So all the green add up to the magic number, up and down. So I just did from left to right, and I animated what it would look like, sort of as a display. And so I'll run the animation here. I don't know about you, but I think that's pretty cool.
Yeah.
And I certainly could have done it up or down if I wanted to. There's more secrets to unlock here. All of these blocks of 8 all add up to the magic number. If I shift it over 1, it adds up to the magic number. As it turns out, any of these, if I choose, are the magic number. And if I shift them along, they all add up to the magic number. If I do it by column of 8, guess what? Adds up to the magic number. And if I choose any of them, anywhere, they add up to the magic number. The reason for this is any block of 4 adds up to half the magic number. So if I choose 2 at any place on the array, they add up to the magic number. And that's true for the other direction as well. Guess what? Ben Franklin did this without a computer as a hobby. Here is a 16 by 16, and it has exactly the same properties, but just double. And I'm not going to go through them all, but that's fascinating. That absolutely fascinates me. A man did this as a hobby, and it's fascinating. I highlighted just this one row. I found this interesting. 49, 48, 17, 16, 241, 240, 209, 208. That's a little bit of luck, I'm sure. It's kind of neat. Okay, so now here's squared magic squares. This is not a magic square, but when I square the numbers, all the columns, rows, and main diagonals add up to 815. Mr. Euler, probably number 1 or number 2 mathematician of all time, discovered this in 1770 without a computer. Okay, so we saw 1 was possible for a 3 by 3. What about for a 4 by 4? Or, I'm sorry, we saw it for 4 by 4. What about for 3 by 3? Well, the answer is no one knows. Is there a 3 by 3 square where I can take 9 whole numbers, square those whole numbers, and get rows, columns, and diagonals to add up? No one knows. The best anyone's ever done is 7. So they take 7 distinct whole numbers and square them, and then they just plug in 2 random numbers to make it work. If you can answer this question, there's a prize and worldwide fame awaiting you. It hasn't been done, and it can't be done. No one's found a solution on a computer. I'm sure as I speak, there's a computer somewhere working on it, but that hasn't been done. Okay, so this is a magic square. It's normal. All the rows and columns and main diagonals add up to 260. When I square them, it's also a magic square. And the squared magic number is that absolutely fascinates me, by the way. Here's a sum product square. This is not a normal magic square because we don't start with 1. But if I add up all the rows and columns, the main diagonals, the magic number is 840. But if I multiply them, all the rows, columns, and main diagonals add up to whatever that number is. What is this? Let's see. This is thousands. This is 100,000. This is millions. This is billions. Is that trillions? Yeah. What comes after trillions? Quadrillion. So is this a quadrillion? Is that what it is? A high school math teacher came up with this in 1955. Okay, so now prime magic squares. This is not a normal magic square because we're not using 1 through 9. But this is all prime numbers from 1 through 67. And 73, sorry. So 73. And its magic number is 111. Who can tell me what the problem with this is? I see a problem. Does anyone else see the same problem? Yes, what is it? 1 is not a prime number. But it used to be. In fact, 1 was a prime number up until, well, some people say really up until 1949. Right? Yeah. So it certainly was considered prime up until the early 1900s. Some of the greatest mathematicians said it was prime, and an argument broke out. Wait, how can 1 be a prime number? Because the fundamental theorem of arithmetic gives us trouble, right? So they changed the definition of prime and said 1 is not a prime number, you have to start with 2. So this is the smallest magic square where 1 is not a prime number, and you have to start with 2. And its magic number is 213. These are consecutive primes. It's not really, well, it's a square, but it's hard to write a square to make it look. So, I'll be honest, I'm taking someone else's word for it because I've not tested all these to be prime. I still find that pretty fascinating. Okay, so this is the area that really interests me. I hope to really be able to study this more as a graduate student. I took a 4 by 4 magic square, or sorry, just a 4 by 4 square, and I started in the upper left-hand corner and I listed 1 through 16. I did the same thing in the other direction, and starting from the bottom left-hand corner, going all the way up, and Same thing. Then I colored each one, red, yellow, blue, green. And this is Duer's 4x4 magic square. And then I'm going to overlay this on top of that. And I notice the numbers 5 and 9 and 8 and 12 line up. I'm going to do the same thing to the green one, and 3, 2, 15, 14 line up. Same thing with the red and the blue. And I get this pattern. Now this is, you think, great, Brian, so what? Well, I did the same thing with a bigger one, and I notice this pattern. It kind of interests me. Here's a different pattern with a different magic square. Because again, this is a 1, 2, 3, 4, 5, 6, 7, 8 by 8. How many unique 8 by 8s are there? No one knows. So I could be here all day doing this, looking for distinct patterns. This is another 8 by 8. So I took this one in particular, and I used just the yellow. I took out the grid, thank you, and I added a black background to make it stand out. I did the same thing with this one, took out the grid, added a black background to make it stand out. And here's a bigger one. This is a 10 by 10, and doing the same process. So there's these unique symmetries and patterns, and I'm very interested in what are these patterns and what can these patterns be made into. As I shrink sort of the pixels down, it becomes, the lines become less and less rigid. So if you had a 500 by 500 magic square, and you use the same idea and I shrunk it down, you could get very distinct non-jagged edges, right? Okay, so there was a physicist, mathematician, artist that ran some experiments. I butcher his last name. Does anyone know how to say his last name correctly? I think it's Chandonnet, I think is how he say it. He's a Frenchman. And he took glass plates fixed on a pivot in the middle, and he ran a bow along it, and it vibrated the glass plate. Then he poured sand on the glass plate, and the sand accumulates in very specific places on these glass plates. This is an experiment that at Western they run in the physics lab. They don't use a bow, they have a special machine that resonates at certain frequencies. And as it turns out, these very interesting patterns develop. These are some of these patterns. We saw this one a minute ago, right? This one we certainly saw. That one's close to something we saw. We saw that one. This one we saw. Any of these, of course, we saw. So if I look hard enough at certain values, can I find something that looks like this using my technique? Right? So wouldn't it be interesting if I could take magic squares and in this special way I've designed and come up with all these different resonances? Now, there's some advanced mathematics going on here that makes these patterns. They're called eigenvectors, something to look forward to. And where all the sand accumulates is where the eigenvectors are equal to 0 because there's no vibration there. Well, a magic square is an array of numbers, and we can find eigenvalues in an array of numbers. So mathematically, I'm pretty confident we can find most of these patterns. So that's what absolutely fascinates me, and I would like to study that more as a graduate student, probably with the aid of a computer. Okay, so why study magic squares? Well, here's a list of some things I thought of that magic squares are being used in. Today we've talked about these things, certainly arithmetic algebra, abstract algebra, artificial intelligence, computer programming, topology, linear algebra, optimization, number theory. So these are some of the main reasons why you'd want to study magic squares. And then finally, I study magic squares because they're fun. All right. Thank you very much. Does anyone have any questions? Yes?
You gave us a pattern for finding any odd number magic square. Is there one for even numbers
I'm very glad you asked this question. There is not one known for even. However, there is known for 4x4s. Okay? So there's one known for 4x4s and any multiple of 4x4. So that's 4n, so I've sticking any number there. So what you do is you draw a diagonal across, and you start in this upper left-hand corner. So anywhere you see the diagonal, don't write the number. So this is 1, but it's the red, so don't write it. 2, 3, 4, don't write it. 5, 6, 7, don't write. 8, 9, don't write. 12, don't write. 14, 15, don't write. Start down here now. Now fill in the remaining blanks. So 1, 2, 3, 4, 5, 6, 7, 8. Wait, I messed up, sorry. 1, 2, 3, 4, 5, 6, 7. This was already occupied. Then 8, 9, 10, 10, 11, sorry, 12, 13, 14, 15, and then 16. So when you take out the blanks, you have a magic square. You can do the same thing with any size 4x4. So you do it for each block. So I did it for this block, and then you do it for that block, and then fill in all the blocks. And then do the same thing. Start with 1. This has a red, so don't put it. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, so on and so forth. Then you start down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so forth. And that works for any 4x4. But again, is this a unique solution? It's not unique. But it gives you one solution. I anticipated this question, so sorry. Is there any other questions? Yes, Mr. Dersh.
Any indication on what you've read that would tell you how Franklin came up with this amazing magic square?
From what he said was, he indicated he felt he wasted way too much time doing this. But it appears to be that he was so good at arithmetic that he says in his letter, I could write them faster than you could say them. So he didn't even have to think, what's 17 plus 49. He just knew it. And so I think my feeling is like Sudoku. If you do it enough, you get kind of good and you kind of see what's happening. And I think that's what he did. He was just so good at the arithmetic, and he got used to sort of what he was looking for and came up with these. Those are not the only two examples. There are, I think there's a book published more for like grade schoolers that gives many, many examples that he did. This is strange to say, but as the size of the magic square gets bigger, it's easier to complete things, right? Because there's more numbers to work with. So there are some, when he was doing 16 by 16, that's fascinating, but I think it might have actually been easier than the 8 by 8, just because there's more numbers to sort of work with. But that absolutely fascinates me. Of course, you can argue about what is a genius, but I think Ben Franklin certainly would make the list of someone who really was an accomplished, genius for real. Yeah.
Do you think that magic squares led to the creation of the game Sudoku, being that all the columns and rows have to have 1 through 9?
Okay, so magic square has a cousin. It's called a Latin square, and Latin squares are where Sudoku came from. That is a very cool topic to research as well, and it has to do with some pretty hard math, which not hard, but pretty serious math, with like abstract algebra. But it came from Latin squares, which are the cousin of these folks.
Okay.
Any more questions? Yes, sir.
Franklin's squares were so amazing to me, and I'm thinking about that in terms of the other patterns that you showed,
Mm-hmm.
part of the physics experiment. And I wonder if do you believe that the patterns were intentional, or were they incidental as a consequence of these relationships between the numbers?
I see. Okay. Well, I'll answer this in a broader way. I think the symmetry of mathematics is sort of God-given. Okay, so when Franklin set out to accomplish this task and these other symmetries we see, I think Franklin recognized the symmetry quickly. And I think he used that to his advantage to find where he was going, because he saw the symmetry and said, hey, I'm going to sort of follow this design. I have not used sort of that method I talked about with a Franklin square because it takes some time to sort of figure out the overlay, and I don't have enough computer programming background to have the computer do it for me, so it really takes some time to think about it. And I'm not the first to come up with that. I mean, other people have thought about that. But I haven't done it with a Franklin square, but it would be interesting to do it with his square and see, what patterns come. Let me go back to his square a second here. It's a little ways back. By the way, I think that's cool. I really think that's cool. Let's see here. When you look at, let's see, where is Franklin? This is absolutely fascinating as well, but when you look at his, ways back here, this one, this one, oh wait, this one is better. Yeah, okay. Again, I think, Franklin recognized he was looking to make a bent row, and I think he recognized the symmetry was happening quickly. I think given enough time, I could accomplish the bent row in one direction, but to do it in every direction that baffles me.
That's what I mean. Is it forced by the act of calculating it, in a couple of different times through there? Does it force the?
Oh, for it to be work out in every direction? I don't think so. I think that, okay, so if you look at this thing as a topological object, so you wrap it around so it looks like a donut, I'm confident there's some topological reasons why it works. I don't know those reasons, but I'm confident that's true. But I don't think, I'm wondering, I should say, did Franklin intend it to be that way to start with, or just realized it was that after? That I don't know. It certainly is true. My mind works, I read from left to right, so I'm going to work from left to right. Well, when he got done, did he go, oh, hey, it works the other way too? I'm not sure, but I doubt it, because I don't think that happened by luck. I think he worked hard to get it to do that. Because, let me back up a little further here. When I look at like this, there was no accident in this. This happened very specifically for that reason. And, you can write a computer algorithm in C+ or Python or any basic program that can do that, and it might take it 20 minutes to find it. Franklin did it by hand. That absolutely fascinates me, and.
Isn't it possible, I'm sorry, maybe I'm exposing my ignorance here, but because of the inherent nature of numbers and the squares and all of that, isn't it possible that once you complete one direction, maybe because of the way inherently numbers are and the squares are, isn't it possible that it just falls into that pattern? I don't know.
And I think that's a possibility, because again, like you said, there is this symmetry that is true with the integers, and it may have well been that way. That when he was finished, he went.
It takes you like trying to force all these directions
To happen, yeah.
sheer will.
Yeah.
I don't care how much time and energy
Yeah.
or how smart you are with arithmetic.
Right.
I can't imagine doing that.
To get it to work, right? And imagine what happens, you get all the way down to here and you're like, no, it doesn't work, Yeah. So no, I believe there is a symmetry in mathematics. I mean, it's clear, So maybe it happened as an effect of getting it to work one way it always worked. I'm not sure. It'd be really interesting to think about. And many of us in this room know there's a lot of heavy mathematics going on here. you know, and it's not more than just adding some numbers together. So, and I don't, you know, I haven't gotten to that point yet where I understand all these heavy necessarily mathematics, but either way, it's cool, right? It's really, really neat. Is there any other questions? Yes, yes, sir.
What's the biggest magic square someone's ever made?
Okay, so that's an interesting question. If you're talking about that a person has made, that's different than they've made a computer made, right? So you can go to websites, there's online periodicals, like online magazines, where people publish their magic squares. And the biggest I've seen is a 24 by 24 that a person actually worked out. Now, a computer, that's a, you know, computer can do it, whatever it wants. It just, this amount of time it takes. So the biggest I've seen is a 24 by 24. So, but you have time over Christmas break, right? Let's see what size you can make. Well, if you had a room like this, you can get a big chalkboard and like, work them out. Yes, sir.
Have you ever counted through 1 through 64 on this and recognized any patterns here?
I have not done that. I thought about doing that, and
If you look down there, you start at 1, you go up over 1 and up 1 to 2,
mm-hmm.
then you go up to 3, over and up 1 to 4,
Uh-huh.
and then
We start with 5. Oh, 5 and 6 are backwards, but
5 and 6 are
but they
down,
certainly are connected. Yeah.
7 and 8, and then 9 to 10 is kind of it's a little hard to see, but
Sure.
it does follow a pattern.
There-
I was just wondering if that.
And it very well possibly could be. Again, you know, there is mathematics is deeply symmetric, and if I'm confident if it was there, Franklin found it. That's yeah, and especially when you're talking about. Oh, sorry. Here, let me.
My man was catching a pattern.
Oh, sorry about that. Here, oh, wait, it'll go through one more time. I don't know how to stop the animation once it starts. There it goes. Okay. So what are you guys thinking about that? Does anyone else have any questions? This is cool stuff, right? And what makes it cool to me is that, you know, a grade schooler can do it and find cool things. And so, I mean, people with PhDs study this too. And that's what's really, really cool to me. Where there's some other mathematical subjects that, you know, don't reach across that broad spectrum of knowledge and abilities, for sure.
Mike, in reference to your comment, there is a question here of whether Franklin actually created square or did he just discover it?
So yes, did it exist before or did he discover it? I believe that he discovered it. It was already there, but he was the first to write it down. So this is an argument in math. Right? It's older than can the computer really prove things? But anyone else? So what do you guys think? You found the pattern? Franklin, these squares fascinate me. They've all really fascinated me, but this one, these in particular really are interesting things. So. All right, well, thank you very much. I appreciate your time and sharing my excitement about Magic Square.